The logarithmic rule is one of the most important rules in the world of integration. When do we use it? If we see a function in the denominator and its derivative in the numerator. If we see any function and its derivative in the numerator, immediately the logarithmic function must come to mind. And we put ln. We bring the denominator and the absolute value of the denominator, which is the function itself, plus the constant c. What does ln mean? It's the same logarithm, but we've chosen the base e. Instead of, as we saw in our previous lesson on what a logarithm means, choosing 10 or 2 as the base, but if we make the base the number e, it means the log turns into ln, just for brevity. The number e, of course, we'll study later its importance and why we chose this number. Let's take examples. Here we have a function and above it its derivative, x squared here, 2x. Immediately we say ln. Here we're supposed to put an absolute value, but since it's an even function, it doesn't matter. Plus the constant c. Here same thing, x cubed plus 3. Above it is derivative, 3x squared plus 0. The derivative of the constant is 0. So a function and its derivative, we put ln and bring what's in the denominator, the function in the denominator as it is here, and we put plus the constant c. Don't forget the absolute value, because here we have a cube. Sine and cosine we'll study later, but the derivative of sine is cosine. So here's the function and here's its derivative. But we just want to know, if we see a function and its derivative, immediately we recall this rule, ln of the absolute value of sine plus the constant c. Now we want to return to 1 over x. Remember the power rule, we said it doesn't apply if the exponent is -1. What does x to the power of -1 mean? It means 1 over x. We can now look at it with the rule we just learned. We have here a function and here its derivative, 1. So immediately we take the function and say ln of the absolute value of x plus the constant c. So now we've solved the problem we had when we were dividing by 0. If we use the power rule, we'd say -1 plus 1, and we'd get x to the power of 0 divided by the new exponent. 0 would be dividing by 0. So we can't use the power rule. So this solved the matter for us. We use the logarithmic function or rule. We still have some simple additional details. If we graph 1 over x, if we graphed it like this in the positive region, we notice there's an area between the function's curve and the x-axis. So it's natural that we keep searching for a rule to solve this matter, and fortunately we were able to solve it with the logarithmic rule. We found here we have a function and here its derivative, and we apply this to it. Indeed, here we have the function and here its derivative. We go to the negative region. We know that log is undefined in the negative region, but here we have an area between the function's curve and the x-axis. That's why we put the absolute value of x or of t. Why? To take the negative out of here. And when we take the ln of -3, it's the same as the ln of 3, because we take its absolute value. And notice here a final observation. The area under the curve or under x, between the function's curve and the x, is supposed to be negative. But since we're heading to the left, the direction gives us a negative, and the position of the area gives us a negative. Negative times negative becomes positive. These are simple details, but what matters to us is that we know this rule. If we see the function in the denominator and the derivative in the numerator, this rule applies.